Welcome to SOH, Best Office Hours Ever, because you are part of it. This is 2024, just 1 year ago, Physics 1, problem number 2. You know that this year, in 2025, the APs are going to change to a hybrid version, and also the number of questions and the time given for the physics exam is going to change. However, the concepts are the same as before, and practicing through previous exams is a good way to learn. Let's look at this problem. There's a design of an experiment, so there is a little bit of wording. And of course, one never knows if it's going to be enough wording, too wordy, or whatever. But we'll try to go through that. As always, let's begin by reading the problem, trying to get the ideas that we will need to use. And if you are fine, maybe in 2-3 minutes you're done, you can practice on your own and come back here with your 5 and let's move on to the next one. If not, we can stay and look at the details of how to write things, or you can just jump to the one that you are most interested in. So let's read through it. We have a student hangs a spring of a known spring constant. So probably this is going to be one of the major things, right? To find the spring constant. Vertically, by attaching one end to a stand as shown in figure 1. The other end of the spring has a small loop, this loop here, from which small cylinders can be hung. In addition to the spring, the student has access only, and they underline it, to a variety of cylinders of unknown masses. A stopwatch, so we don't know the masses, unknown masses, a stopwatch, and a digital scale. Well, the first thing that surprises us is that, well, unknown masses, but we have a digital scale, so we can measure the masses. The other thing is that we have a stopwatch. So a stopwatch measures time. Usually with a spring, we would like to measure length, right, the stretch, with a ruler. But we don't have a ruler, so only these things. So if we don't have a ruler and we have a watch, then we're going to measure time, we're going to measure motion. So it's going to be a little bit more complicated, right? So it's going to be with motion. Indeed, in order to know the constant K, you may figure it out. It would be simpler to hang the cylinder, let it fall slowly, and measure the stretch with respect to the initial position, and apply Hooke's law, and get to know how much the constant is, right? So, but in this case, we don't have a ruler. I suppose that, well, whatever, we have a stopwatch, and we're going to do it with a stopwatch. I think that this would be nice to do both experiments and compare the results to see which tool has a better accuracy and a better precision. So maybe the ruler has lower precision because it's harder to read, what's the tick, but is more accurate because it's simpler. And the stopwatch has a higher precision because we can just tick and it has like milliseconds, right? But the accuracy is not so good because it's harder to, when we press with the finger and when we see the cylinder crossing some point. So that would be a great experiment to understand the difference between precision, accuracy, and how to deal with that in practice. But for now, we are AP test, and we have to deal with this, get a 5, and then move on to all the things that we are talking about, right? And you could write that, and that will be awesome. So let's see, what do they want us to do? Design an experimental procedure, so this is going to be a bit wordy, and to measure the spring constant K, okay, with those tools. Then in the space below the table, first define a symbol, so we will have to define some symbols, and in the space below the table, so define a symbol, in the space below the table, which table? This looks like it's after, okay. Describe the overall procedure. Okay, provide enough detail so that another student, basically that the level of that if you give this to someone else, that he or she can replicate it, okay? And you may include a simple diagram if needed. It's not necessary, don't feel obliged to. Okay, so the first thing to do is, well, as you know, we have the stopwatch and the digital scale. So we have the digital scale, let's measure all the weights of the cylinders, right? So the first thing that we could do is, first step, measure the weight, let's say of one cylinder. Let's begin with one cylinder, okay? Because usually in an experiment, you want to do it once and then repeat it more times to control the error that you may have by doing that experiment. So let's measure one cylinder. Now remember, we do not have, this is additional, but we do not have a ruler, okay, to measure the stretch. that's kind of a justification of what we're going to do. What we're going to do next. Okay, we don't have a rule to measure the stretch. So, but we have a stopwatch. So this means that we are going to do something with motion. What can we do with motion? Well, that's where the tricky part comes. You may hang it and then, like push it down a little bit and let it oscillate, and then measure how long it takes to do these oscillations. So we need also convention on when to start ticking the time. You may say, well, when I let it go. Yeah, but maybe tricky. So we can pull it down, and then once we let it go, it's at the bottom, right? Then we start ticking the time. And a full cycle it's at the bottom, goes up and comes down. That's a full cycle. That's one period. So we can measure not one period, but maybe wait 1, 2, 3, 4, 5 until 10 or 20 and stop the clock. That might help us measure with a little bit more of precision what's the period of the oscillation. Okay, so let's write that. So the next thing that we're going to do is to hang the same weight, the same cylinder, right? We don't want to change it. Let's be clear, just in case. It's a different cylinder, the same one. Take it easy. Then stretch, the spring down a bit, and as we let it go, we start ticking time with the stopwatch. We're not going to count aloud, right? But let's say it. Yeah. Maybe we get 1 point down because we don't have it. Okay, stopwatch. Okay, so then we don't just wait once to have the period, because imagine that it's very fast. So it's very 1, 2, 3, 4, right? So let's at least count like 10. Then we wait until the cylinder has completed, and this is a little bit arbitrary, right? Let's say between 10 to 20 full, that's the important thing, full cycles. This is very important, okay? This will help us measure the period. So then we stop the stopwatch and estimate the period as period equals total time elapsed, right, since we started, divided by n, the number of full cycles. And that's your period. Why do we do that? You cannot hear, if you remember, that would be great, that the period in a simple harmonic oscillation is 2 pi the square root of m divided by k. So there is a relationship then between the mass that you measure at the scale and the period that you're measuring with the stopwatch, and this is the unknown, right? So we are having kind of two numbers, and we want to find the third one. So let's complete the table. So with the stopwatch, we're going to measure, let's say, the period of oscillations, right? Period of oscillations. It's better to say period of oscillations, not just time elapsed, because we are going to use the formula with the period. Let's say t, and then with the digital scale, the mass, right? Mass of the cylinder, mass of cylinder, or cylinders. Okay. Now, what's important is this would give us one measurement, one period, and the mass of the cylinder. We could do it like instead of 10, 15, 20, and repeat the same experiment with the same cylinder. That would be a good idea. But in order, we don't have much space, right? So in order to finish this, we can say that we could repeat the steps 1 and 2 with different cylinders. How many? I don't know, all. If we have, plenty of time, if it's the cylinder party, that we can spend the whole weekend with this, okay? But otherwise do 1 or 2 more. But the point is that with different cylinders, and that's it. To control, if you say this, to control errors, that would be awesome. If you do this, you're done. You're the next best experimental physicist ever. Okay, so that's basically it. I didn't do a diagram here. Maybe we could do it with a full cycle. There's not much room, so that's how it is. But this is, I think, pretty good. Now let's move on to the next one. It says indicate the quantities that could be plotted so that we need a plot to produce a linear graph. We need a linear graph. If you remember, our relationship was like something like this. This is not a linear relationship. We have a square root, we have a division, so that's not a linear graph. So that's very important. Whose slope can be used to determine the spring constant K. So that's the goal. The goal is to determine this guy here. Okay, but that's the unknown. Of course, you could say, well, okay, let's do the square of this, 4 pi squared, m divided by k, and I want to find k, so this is it. All this is correct. Another relationship could be, instead of this one, m equals k divided by 4 pi squared t squared, right? All of these are correct. Now, the point is, we want a linear graph, and we want to find k. So this gives us k. That could be good, but there is a division here, right? So here we have a division. So it's not linear, Okay, this is a linear relationship between these two guys, linear. But k is in the denominator. And so what? Well, indeed, it's okay to have it in the denominator. But when you deal indeed with propagation of errors and so on, you will need to do the reciprocal, and the propagation of errors becomes more cumbersome than if it's just in the numerator. So it's not, this is good, t squared and m are linearly related, but k is in the denominator, which is our unknown. No big deal, but we have to choose the easiest one. And indeed, this is the easiest one because we have a linear relationship between these two guys, linear. And this is the slope. So the slope and k, what we want to know, are directly, not inversely, directly related. So it's the easiest one. It's not that the other ones are wrong. All of them are correct, but we choose the easiest one, and especially they want a linear graph. So let's do this. So let's do a graph. We choose the last one. We choose this one. So we choose this one. Let's write it here to be sure that we have everything clear. So that would be like y equals slope times x. So this is x then, and this is m. And I don't know, you would get some measurements, right? And then you would have a line. It would go in principle through 0, because if you don't have any mass, it will not oscillate. So 0, 0, right? 0, 0, that makes sense. So it would be something like that. And that means that the vertical axis is m, so the mass of the cylinder, right? We have more than one. Then the horizontal axis will be the square. It's not the period, it's the square of the period, because we want this linear relationship. This is a very standard method that you have a formula that is nonlinear, but you want to find out something in the formula, then you make a transformation to bring that into a linear fashion, and then you use the power of linear fitting, which is a tool in any calculator and everywhere very well known, and so on and so forth. So that's a very standard procedure to solve many experimental problems. Briefly describe how the slope of the graph, okay, so, well, the slope of the graph is just k 4 pi squared. So you could say that your k is going to be the slope of the best fit, and this is the best fit slope, okay? And that's amazing, and that's it. So that's fantastic, okay? All good. Now, what's the next thing that we have to deal with? Well, in a different experiment, okay, there's a different experiment, that's so long. The student attaches one end of a spring to a force, okay, all these things. So we have a force sensor and a motion detector. I don't know, all this is amazing, but the point is that we have a mass of 0.25 kilograms, and we have this graph and this graph. I mean, amazing, amazing. If you want, maybe find it in Amazon and try it on, but we're just going to go to the graph and that's it. So no commission on Amazon, no? Anywhere. So the student places a motion detector to the right of the car, blah, blah, okay. The following graphs show blah, blah, okay, fine, please, let's move on. So using the data in the velocity time graph, calculate the change of kinetic energy. Okay, let's go to the point. So kinetic energy is 1/2 of mv squared. Do we have the mass? Yes, the mass was 1/4 of a kilogram. Do we have the speed? Well, what time do they want here? Yes, 0.3 meters per second. What about the next one? 2 seconds. Be careful because, yeah, here, oh yeah, okay, 0. Awesome. So the change of kinetic energy is going to be the kinetic energy at time 2.0 seconds and at time 0.5 seconds. And then we have 1/2 of 0.25, 0 squared, I love 0 squared, is 0. And then 1/2 of 0.25, and then, well, 0.3 squared, that's not so cool. But what we have is 0 minus this quantity here. You can use the calculator, and then this gives you minus 0.01125, and that's very important, joules, okay? Joules is the unit. If you use the mass in kilograms and the speed in meters per second, which is the international system, then you have that energy, kinetic energy is the joules, okay? That's very important. So that's fundamental, otherwise you get some points down. What about the significant digits here? You know, we have 4 significant digits, 4 significant digits. I mean, 4 significant, right? We have more, we have the zeros, but 4 significant digits. How many do you need to know for the AP test? It's in between 2 to 4. So it's kind of a little bit free. They don't enforce that you do it right. In this case, if we trust that these numbers are exactly correct, that's 4, and it's infinite precision. But we know that it's an experiment, so there may be some error. So once you know the error, you could round this up. But you can leave it like that. It would also be fine to give this answer like 1, 1, and then instead of 25, 3. Remember that if you have a 5, you round out up. And if you have less than 5, down. Okay, but 5, which is in between, goes up. That would be joules. It's also cool, both of them. Okay, let's move on. Using the data in the force diagram estimate. Oh, this is a good question. Change in momentum. This is a good question. Why is a good question? Because it's a bit harder. What we have is it's not so obvious just to read the numbers on the graph. We have this is a fundamental. You know, like this is the net force. That's the second Newton law. That's indeed what Newton brought new. The first law and the third law. The first law is that if there is no force, an object continues in rectilinear motion. That was Galileo already. And the third law that to any action there is a reaction. So you know, action, reaction. Then that's from Descartes, indeed, a philosopher and a physicist too, that precede Newton. But this was his law and how to describe the change in motion. So P is the momentum, linear momentum. And that's how Newton described the change of linear momentum. So what we have is to invert it. So the change of linear momentum is this thing. It is the integral of the net force between 2 times. This is a fundamental relationship that if you have not seen it yet in class, have it there, okay? Maybe you have seen the first one for sure, you know, this first one for sure in class, but this is also very important. So what do we do here? Look, this is the area under F. So the change of momentum between these 2 times is going to be, you know, let's write it like a pro, right? 0.5 seconds to 2.5 seconds of f of t dt. That's amazing, but this is the area. So if we go here, we have all this area and all this area. How are we going to compute it? Like that, 0. Yeah, we love 0, just because these 2 areas are the same, so they cancel each other, right? This is positive, this is negative, so they cancel each other. So indeed, what the conclusion here is that P, the linear momentum, does not change between t equals 0.5 seconds and t equals 2.5 seconds. 2.5 seconds. Okay, does not change, and that's it. Great, bye. Now, the last one, do the data from the velocity. Well, here is just to remind us what is the expression of the linear momentum, which is this, the mass of the object times the speed. Indeed, with a vector, it would be with a vector, but we don't need the vector in this case, okay, so let's not complicate our life. So what is the linear momentum at 5 seconds? It's going to be mass times the speed at 5 seconds. And if we go here, we get it. It's 0.3 meters per second. So you have 0.25 times 0.3 meters per second. So this gives a number. But look at this. So they say that, briefly explain why, right? I mean, if you want to be thorough, then do everything, you know, like I'm doing here, because there is no doubt that you understand everything, and here, the same speed. Notice that it's the same, it's positive, so it's exactly the same. It's not like negative or whatever, it's exactly the same. And this gives a number, okay, indeed 0.075, and the unit is, it doesn't have a name, unfortunately, it doesn't have a name, despite that is so important. It could be Descartes, because he was, you know, the guy that that prefer this quantity to describe physics, but it has no name yet. And well, so you can see how the change of linear momentum, is going to be zero, because it's the same number, it's 0.075 minus 0.075. So yes, we confirm this, and we confirm that we get an A++ everywhere here. Okay, that's our goal, and we have it everywhere. Thank you so much. See you in the next one. Let's have fun. Bye.